Good afternoon, everyone. Let me know if I am audible and screen is visible.
Good afternoon,
Yes, sir.
sir.
Thank you. So let's start with our. I'm sorry for I have to postpone a little bit the class. Today we'll start with IPv6, which is the next version of protocol from IP. By default, what we use in internet is IPv4. IPv4 has identified limitation that number of addresses are limited and we need more address space, which will come in a short while. And that was the primary motivation or reason behind coming a new protocol called IPv6. So these are the few resources which are other than your class textbooks. Those who are interested in knowing about IPv6 detail, history, evolution, lot of things, they are very good resources. You can go through that and see those. So why do we need more address space? What is the address space available in IPv4? Anyone like to answer? When I say address space, how many possible IP addresses can be there in the IPv4? Nikita, you all studied
Yes,
IPv4 addressing last semester, yeah.
yes, sir.
What is the total number of possible IP addresses we can have in IPv4?
So four. I
No.
don't. I don't know, sir. Not.
Kritika Vasist,
So I don't know, sir.
Chandan,
Sorry, sir, don't know.
what is the number of bits in IPv4 addressing?
32.
32.
32. So what are the max possible values you can have?
38.
32?
Sir, 2 power 32.
2 power
Yes.
32, and how much is that in decimals? 2 power 32 is about 4 billion. That means maximum possible IP addresses that you can have is about 4 billion. Now, if you were to give one IP address to each human being, will that be good enough? Will we be able to meet the requirement? Let's suppose each human being we give one unique IP address. Will we meet the requirement? Niharika, what is the world population today?
Sir, 9.9 billion.
No, you are way too off.
7.8 billion.
7.8 billion or 7.5 billion, whatever. So that means we have world population is 7.8 billion. Possible IP addresses are 4 billion. That means we can't even assign one IP address each to a human being, even if we want to. And that indicates shortage. The other thing is you look at each user has number of devices with IoT coming up. Each device needs addresses. So we are inadequate as far as IPv4 is concerned. And when we read some of the references I said, and one of the books says this addressing problem came because of India and China, because the moment these people in this country started using internet, we started feeling shortage of address space. Till the time we were fine. So the comments apart, We need more addresses because it's expected that each user would have some maybe 20, 30 devices. You take a watch, phone itself with three interfaces, your Fitbit, your anything else you take, everything needs connectivity. Now we talk about your button, your shirt, your shoes, your anything you take, you will have this some IT device sensor connecting to internet. So while we addressing the shortage of address space, we could also address the some shortcomings which was there in IPv4. One of the major thing what is called security. Is IP protocol secure? Anyone? Is IP protocol secure? Monica, does IP protocol offer security? Anyone? Chatra? IP protocol does not give any security. It is the best effort delivery. So when IPv6 was thought, I hope my mic is on. Yeah. So we could address the security part, which we'll study in IPSec in a short while. IPv4 would do NAT, called network address translation. That, for example, when you access from home, your IP address typically you'll find as 192.168 dot something or 10.10 dot something. And the moment you access internet, your internet router or gateway connectivity sends a packet with a different public IP address. And that means your home router or your ISP router or college router is doing a called network translation from private to public IP. And that was done because we don't have a many address space. So we hide all those. So with that, we don't need the NAT. Can we simplify the header format? The what is the min size and max size of the IP header? Anyone? What is the min size and max size of the IP header?
Maximum.
How many bytes maximum can be an IP header, and what is the minimum number of bytes in IP header? No one? Does anyone remember IP header format? I mean, I'm not teaching IP because they're not part of a syllabus, and that we would have covered last semester. If somebody still want to review and don't understand, talk to your class rep and I can have extra classes and explain those. But as far as course is concerned, IP header, NAT details are not.
Maximum 16 bit.
How much?
16 bit.
No. Minimum is 20 bytes of header and maximum is 60 bytes of header. And now with options, it could be anything from 20 to 60 bytes. And because header is the variable size, processing always takes more time. If you have a fixed header size, processing becomes efficient. And so can we do away with the variable size header? IPv4 allowed fragmentation. For example, if you're getting a packet, let's say on fiber, which the packet size is 8 kilobytes, but packet going on Ethernet, which packet size is 1500 bytes, that means packet has to be fragmented. So IPv4 you can do that. IPv6 you can't do fragmentation. So and fragmentation issue is if you do fragmentation, It has to be reassembled at the receiver, and then some router has to look at because of NAT, and that will cause a much bigger problem. So can we do away with fragmentation? And these are the requirements that led to design of IPv6. So what you see is a IPv6 segment structure. First field is a version. To differentiate 4 bits, if value is 4 meaning is IPv4, if value is 6 meaning it is IPv6. You may be wondering what happened to version 1, 2, and 3, and what happened to version 4, version 5. So when IP started, it became as an offshoot of TCP it was separated from TCP in 1980. Till that time, TCP has gone through 3 revisions, and hence when it split it became version 4. That's how IPv4 became popular. Version 5 was defined for protocol called ST2, streaming transport 2, but that never took off. But 5 was taken, so cannot be reassigned. So next version given was 6. So, and then your priority, there is no priority field in IPv4. If you want to treat different traffic, voice traffic is different, video is different, file transfer to different priorities, it can assign. How to identify a traffic? You can assign a flow label. Let's say you're having 3 different conversations. You are watching a live TV match, you are chatting on, doing a video call on WhatsApp, you are hearing something else. So each network connectivity or flow, you can define a flow, identify a flow label, and this support was not there. This flow helps you prioritize the traffic and quick delivery. So these were given in IPv6. Then of course the payload length meaning size of the data. The next other meaning like in IP protocol you had what is the next level header. So it goes to TCP, so it will go to UDP or SCTP, indicate what the next header, and that is that field. Hop count or hop limit. Each time router forwards a packet, it decreases the value by 1, and the moment value becomes 0, it discards the packet. And this is done so that packet does not rotate in the internet throughout. Then we have source address and destination address, each of 16 bytes. So if you look at 4 byte first word, 4 byte second word, 16 byte third word, and 16 byte the destination field, total becomes 40 bytes. And so IPv6 header is fixed 40 byte. And we have already next header indicate TCP, UDP, or you want to put options that would indicate. Other things you look at the changes, so a lot of things have been removed from IPv4. First thing you look at the checksum. What is checksum used for? Any clue? We had discussed checksum. IPv4 had a checksum. What is checksum used for? Bhavani KG? Lavanya? Dhruv?
Yes, sir.
Can you go on mute if you're not in the part of the call?
Sir, it is used for error detection, sir.
Yes.
Hello, can you hear me?
Yeah, I can hear you. Answer is right. It is used for error detection. And now every time you do error detection, it causes a problem. What happens is in IPv4 there's a checksum, and checksum included using hop count. So each time router forwards a packet, it decreases the hop count by 1 or TTL and recompute the checksum. Recomputing checksum and adding it because hop count has changed, checksum would change, so it is recompute. And that becomes too much computing work. So if you avoid the checksum, our processing of packet would be faster. When IPv6 checksum is removed, IPv6 has a fixed 40 byte header. It is the options filled in IPv4 that made it variable length, so options are removed. Also, we had updated ICMP in IPv4 stack. We had called IGMP Group Management Protocol, which has been kind of merged with ICMP. ICMP also primarily used for checking reachability, network diagnostics. So all that has been merged into ICMP v4. And even though security and mobility was added on in IPv4, IPv6 is designed to support without causing any extra modifications. So you can, IPSec can be part of IPv4, you can define it, whereas in IPv4 is kind of add-on, mobile IP is kind of add-on, but here this can be defined as part of IPv6. Looking at the IPv6 addresses, they are 128-bit addresses, and that means you have enough addresses, and if you read the book says this address space is so huge that it is 2 raised to power 128, and that means even if you were to assign one IP address to each grain of sand, you still have enough address space. So leaving away the way we write it is in called hexacolon hexacolon notation. The in IPv4, how do we write IPv4? So let's look at, if you look at, this is my IPv4 address 192.168.1.2. What is this format representation called? It's called DDN. Can anyone explain what DDN stands for? Anyone? I think you guys need to do some homework. Don't just come to the class simply and come and listen and this thing. As I said, attendance is I'm not really bothered about. You can spend time, you learn a lot. That simply becomes a one-way delivery. We have limitations with online, so but if you can be interactive, you'll be much better off. This format is called dotted decimal notation. Each byte is represented in decimal number, separated by a dot. So you have 3 dots, 4 values, each with a byte. And hence this notation of IPv4 is called DDN, dotted decimal notation. IPv6, we write 2 bytes as in hex format, separated by a colon. So this is my IPv6 address. So if you look at your machine, Windows, laptop, you would always have both IPv6 and IPv4 addresses. So written in the form 4 bytes colon 32 bytes, which comes in 4 digits, because each byte gives me 2 hex digits. So 4 hex digit colon 4 hex digit and so on. So what you see is FDEC colon 0074 colon 0000 colon 0000 and so on. Now look, there are too many zeros. That means writing simply wastes too much time. So can we use a shorthand notation? So there are 2 ways you can shorten the address writing. One is any variable leading zeros, for example 0074. We can omit the leading zeros and this becomes 74. If there are contiguous zeros, you can avoid those contiguous zero and represent by double colon. So this is avoiding leading zeros. So 40 becomes 1, 40 becomes 1, 0074 becomes 74, and this 30 can be skipped with simple double colon, and that becomes shorthand notation. If we look at our loopback address, for example, this is my loopback address for IPv4, which is 127.0.0.1, and here we are writing colon colon 1, meaning first 7 words are 0. So we can write a 0 colon 0 colon 0 colon 0 colon 0 colon 0 colon 1, or we can write double colon 1. That means whatever words are missing, replace them with 0. So this is shorthand notation. So like we ping 127.0.0.1, it works fine. We can do ping 6, that we're using IP version 6, and we can say double colon 1, and you get the answer. It is same as writing 0 colon 0 colon 0 colon 1. Even this, I hope this should work. Yeah, which basically becomes same because all this 7 bytes continuous zeros can be represented by double colon and we are done. Same way, if we were to represent just double colon, that means unspecified address. The address is not assigned to anybody, and we'll look at. In IPv4, you had a unicast, multicast, and broadcast. Unicast uniquely identifies. Multicast is a group of people among few select people, and broadcast is all. Any cast is an address which is given to many people, but when you send a packet, it will go to the nearest one. And that is what any cast would mean. So whichever is nearest, you basically it covers all. So this address belongs to many hosts, but when you send a packet, it will go to the nearest, and that support is there in the IPv6. And now it has been implemented IPv4 as well. For example, when you put a DNS server address as 8.8.8.8, there are many servers with 8.8.8.8 address in different countries, and you go to your own country, but also implemented in IPv4. But as a notion, it's supported only in IPv6. Other is the address space we looked at. When you make a DHCP request, you don't know your IP address, you put in 0. Same in IPv6, either you put 0 colon 0 colon 0 colon 0 colon 0 colon 0 colon 0, or we can just write double colon. Or similarly, loopback address, we can write double colon 1, very similar to the loopback address in IPv4. Having done this, let's say we move to IPv6. How do we move from IPv4 to v6? Given that internet has grown so large, too many people, we can't have a flag day, meaning we can't fix one day and say everybody will move from that day onwards to IPv6. We can't say effective December 1, 2020, every machine will talk to IPv6 only. That's not possible, not even feasible. So that means we need to have a transition strategy. Gradually, can things be moved? And that is what it basically says, how do we turn? The three strategies were defined. One is called dual stack, other is called tunneling, and third is called net64 or address translation. I haven't seen address translation in your book, so I'm not sure it's part of your course, but dual stack and tunneling is very much part of the course. Dual stack means a machine has both IPv4 and IPv6 addresses and uses both concurrently. For example, we use my laptop. If I use ping command, it uses the IPv4 address, and when I use ping6 command, it uses IPv6 address. So both IP stacks are available, both can be used, and that is what dual stack means. That means, and the dual stack, the IPv6 is available since Windows XP, that means since mid-90s onwards. And that is when this is available. And the way it works is, if both are available, then which one should you use? When you make a DNS request, if DNS response contains both IPv6 and IPv4, then use IPv6. If DNS response does not contain IPv6, then you use only IPv4. And that's the way dual stacks works, and both of them exist simultaneously. You can look at a lab machine, note down the IP addresses, ping, and you can reach and access. That also would work. So when doing a socket programming, you can even try using IPv6, and that also would work equally well. IPv6 is available part of every OS, whether Linux, Windows, Mac, all variant of Windows, XP, Windows Professional, Windows 7, Windows Vista, Windows 10, Windows 8, Linux, Ubuntu, CentOS, any versions, Red Hat, Mac. This is available. It is available for more than 20 years, but it has not taken off because it is not backward compatible with IPv4. Had it been backward compatible with IPv4, it would have been transited, adopted. So this is one lesson we need to learn. When you develop a software, when you develop a new feature, do not take away the old feature. We have to have old feature working and new things should coexist. Then takeoff would happen. Otherwise, discarding old one and getting a new one, it may be nightmare and challenging. The other part is IPv6 is we are making changes only in the IP layer. We don't need to make any changes in the data link layer or nor in the transport layer. So TCP can work as it is. Your data link work as IP. So either we can use IPv4 or IPv6 or even both, two different packets. Next approach was tunneling. Tunneling meaning if there is a machine called IPv6, there's other machine with talks only IPv6, but in between system there are only IPv4 routers, for example, internet. Then can I talk? Can I communicate using IPv6? Because I'm talking only IPv6. My destination talks only IPv6, but all my intermediate router talk only IPv4. And that can be done when we use called tunneling. That means between the two end systems, create a tunnel. So if you don't set up a virtual connection, it only involves encapsulation. So two endpoints now shortly configured, two endpoints don't talk to each other. They only encapsulate a packet. So you send the IPv6 packet, and that packet is encapsulated in IPv4. That means whole IPv6 packet is sent as a IPv4 datagram and send it out, and that is how the basically packet goes. This example would explain you. Let's have a system A which is talking only IPv6. I have a system F which talks only IPv6, and A want to talk to F using IPv6. Now A in a network which is connected with a router B, similarly F is another office network connected with router E, and these routers are connected using only IPv4. Now A and F talk only tunneling. I mean they talk only IPv6. So they send a packet out to the next hop B. So B and D will set up a logical tunnel. Logical tunnel meaning they are not doing any handshake, they're not exchanging any packet to set up the tunnel. B would simply take IPv6 packet, encapsulate as an IPv4 packet, and send on this link. So each router would see whole packet is IPv4, it will route the whole packet as IPv4 and send it out. And when the E receives it knows it is a IPv6 packet encapsulated, it removes the IPv4 header and delivers. So you can look at the following way. A sends a packet to F using IPv6 to identify some flow X, source A, destination F, and your data part. This goes to router B, the next hop. B takes the whole packet, IPv6 including the header, takes it as a payload to IPv4, this is called encapsulation, puts in own IP source address as source B, put destination IP address as E. So these both B and E are IPv4 addresses and sends on the internet. So all the internet router, as far as they are concerned, they only look at the IP header, which is IPv4. So for them, it is IPv4 packet. They route as it is. And when the packet comes to E, it knows that we had already configured a tunnel. This is IPv4 packet encapsulating IPv6. So it remove the IPv4 header and send this packet as IPv6 to F. So A and F basically send the communicate to each other using IPv6, and this is tunneling concept. Next is called Net64, which I don't see in a book, but I'm covering it so that your transition state as your IPv6 becomes complete. This is required when one machine talks only IPv6 and other machine talks IPv4. In dual stack, either both machines talk IPv4 or both machines talk IPv6. In tunneling, both machines talk IPv6, but we have a case where I got IPv6, but I need to talk to somebody which is IPv4. That means we need some gateway in between which will convert IPv6 header to IPv4 header and vice versa. And that device that converts IPv6 packet to IPv4 and vice versa is called Net64 device. That means network address translation from IPv6 to IPv4. And that's the way it works. But since the two header formats are different, like there is no priority or flow label in IPv4, so when we translate, we lose that information. Similarly, there is no checksum in IPv6, so even though IPv4 would give me a checksum, it is meaningless because IPv6 there is no checksum field. So some fields can be used, but not all of them. IPv4 a type of service bits, which is called DTRC bits, delay, throughput, reliability, and cost, which has been kind of mapped into what is called priority, but not exactly. So in general sense, when you use net64, it was better set to 0, checksum already get added. And if you want to do like options in IPv4, some of the options can be supported by extension header, which is the next header field we have in IPv4. Diagrammatically, if you look at, there is a machine that talks only IPv6, there is a machine that talks only IPv4, and we need a box which on this side will talk IPv6, on this side talks IPv4. So when this machine A sends a packet to B, A will only put IPv6 address of B, even though it doesn't IPv6 address, but is assumed IPv6 address, send this out, and this router FA0 will know that this is the IPv6 logical IPv6 address corresponds to actual IPv4 address, and it basically puts that in. So this net device needs to know the mapping. Similarly, when this PC responds back, it will respond with only IPv4, and when the gateway receives IPv4, it need to convert back into IPv6. So need to have a mapping, and that's the job of this NetPT device to do the mapping. As I said again, I'm including it so that I can cover the whole topic of transition, even though I don't see any mention of this in your textbooks. Next subtopic of the current class is called IPSec. IPv4, there is no built-in security. And if you want to do secure communication, like in today's, almost everybody working from home, so anybody want to connect to corporate network, you need to have a secure tunnel. And by default, we all use called IPSec tunnel. IP was designed in 1970. It was primarily for academic world, and there itself were too many challenges, how to work with different data link layers, bandwidth, packet loss, itself were daunting challenges, and adding security would have become a nightmare. So that you do too many things, it may not work. So it was kept simple, and security only came to internet as an add-on later on, only when commercial things started. Till that, so till about 94, 95, there was no security really. It started with Netscape 3, and then SSL 3. That is where we started security, and other things came up. When you use IPsec, it basically gives me a tunnel between the two end systems, and all the communication that happens on this tunnel is encrypted. That means if somebody sends a packet, this tunnel endpoint will encrypt it, and other people will see it as a normal IPv6 or IPv4 packet, but because of encryption, they can read the data, but they can't understand it. And that's the kind of security IPv6 provides. IPv6 is end-to-end between two hosts, and the requirement is no intermediate routers need to understand IPsec. So once a tunnel is set up, this IPsec tunnel basically requires a handshake. When we do IPv6 tunnel over IPv4, it was only encapsulation. That means taking an IPv6 packet and putting inside a IPv4 as a data packet. That is encapsulation. Something like I give you a letter, you put this letter into another envelope, that is called encapsulation. At the destination end, you remove the outer envelope and give the internal letter to the recipient. That is encapsulation. Other term you see is encoding, how to convert from one format to another. Like we have seen base 64 encoding, given data, we take 6 bits, write into printable character. So encoding is second. When you talk of encryption, you require a key. Using some key, we encrypt a data, and that means decryption also requires a key. If receiver doesn't have a key, you cannot decrypt, and message would basically be lost. So three different things: encoding, encapsulation, and encryption are different. You should be able to understand and differentiate. IPSec provides encryption at end-to-end, and once a logical tunnel is set up, this requires a handshake. Handshake means the one end will talk to the other end. Like for example, work from home. All the corporate user, when they enable IPsec, the machine talks to the corporate IPsec server, sets up IPsec tunnel, agrees upon few parameters, and once connection is set up, then only any packet that goes from TCP will always go under this tunnel, IPsec tunnel or VPN setup, which will be encrypted and things can break out. So it basically provides security with encryption. Sender will encrypt the packet, receiver would decrypt the packet, and it also enables receiver and sender to verify that packet is not corrupted. So that means IPsec has to provide some basic services to make sure that there is packet delivery on your tunnel securely. So the services IPsec provides is first is cryptographic agreement. That means the two one need to agree upon what cryptographic algorithm they would use, what would the key size. For example, should they use dash, should they use 3 dash, should they use RSA, should they use ECC, elliptical cryptography, or anything else. And even or AES, advanced encryption security, and even with AES, should it be 128-bit key or 160-bit key or 256-bit key. So you negotiate during the connection setup, during the IPsec session setup, you negotiate so that we agree upon the which cryptographic protocol and what is the key size. Second is you do the encryption of the IP datagram. You can either do that encryption only on the IP headers, or you can do encryption of the whole packet. It provides both the support services, so you can do that. And to make sure that nobody has tampered the packet in between, you always include a checksum. So after you encrypt the packet, you add a checksum value which receiver can use to compute is the packet corrupted or is packet is still the same. If packet is corrupted, that means when it computes the checksum value will be different from the received checksum and packet will be discarded. It also provides protection against spoofing. Machine A cannot send a packet to C saying I am B. So receiver can always authenticate the source IP that whosoever sending source IP, it really belongs to that source and it provides that kind of service. So namely, IPsec provides 4 services: cryptographic agreement, that means agree upon the algorithm, agree upon the key size, then the encryption, sender would encrypt the packet using the cryptographic algorithm agreed upon and the key size, and receiver would decrypt it. Then we have integrity, sender has to compute the checksum, send along with it, receiver uses to verify if there is any corruption, any tampering, and lastly, if receiver wants can verify the sender that IP really belongs to the sender and not to somebody else. And basically, when this setup channel is set up or IPsec connection is set up, TCP UDP remain transparent. They simply give to a network layer, and network layer will encrypt do the job. So there is no change in TCP, UDP, or HTTP required. They will work as it is. So to summarize what we discussed, we started with IPv6 addressing, and we said it needed because IPv4 is sort of address space. Even though using NAT, we try to mitigate it, but still we can't allocate IP address. And with IoT coming up everywhere, if we need to reach everyone, we need a unique address which IPv4 can't provide, and hence we came to IPv6. When we added IPv6, we also tried to address some of the shortcomings on IPv4, like remove the checksum, make the fixed header size so that it can be faster processing, and for prioritization traffic, identifying a particular kind of packet transmission to introduce priority and flow. And address notation is used called colon hexadecimal notation. That means each 2 byte written in hex format separated by a colon, which is different from IPv4, which is DDN dotted decimal notation. Then we discuss 3 transition strategies. One is dual stack. That means each machine has both these stacks simultaneously, and it can talk both IPv6 and v4 and we have seen that as well. Next was we had IPv6 tunneling. That means carry IPv6 packet on top of IPv4, and IPv6 tunneling does not require a handshake. It only needs encapsulation. Sending router will encapsulate given IPv6 packet, including headers, as a payload to IPv4, and the other end will remove the encapsulation part, the IPv4 header, and gives IPv6 packet to the recipient. Third transition was NAT64. That means till everybody moves to IPv6, there will still be some host that only talks IPv4. And so machine which has configured IPv6 should be able to talk. And that means we need to have some gateway that converts the transition or mapping from IPv4 to v6 and vice versa. IPv4 has some options, and some of them can be supported by extension header with the next header field. Then we say IPSec, which is actually connection is set up. You do a handshake between two endpoints, and once the connection is set up, the all packets are transmitted over this connection using the agreed upon encryption, but there is no change in transport layer protocol. TCP UDP continues to remain same. It is only an underlying IPsec layer which does the encryption and provides security. And we also look at as a transport mode, meaning IPsec carries transport load of transport layer. It provides 4 services. First one is agreement upon cryptographic keys, cryptographic algorithm. Keys has an algorithm. Second is does the encryption and decryption. Third is integrity check, and fourth is authenticating a sender who says who it is. That's all for today. So we are done. There are a few more slides which I've added. They're not part of a lecture, but as part of completeness, I've given you so you can do the exercise, identify and work out. That will be helpful. And I can talk about ICMP, but again, since we are not part of the course, I'm not covering it. Those who are interested can go through and maybe can discuss separately if they're interested. So I'm done with lecture. If any questions, let me know. Otherwise, you can drop it.
Sir, what is that integrity in IPsec transport mode? What does it mean?
So see, transport mode integrity means when you encrypted the packet, after encryption, you compute a checksum and add, like CRC field or some checksum field. So when receiver gets the packet, if packet is corrupted, it will compute the checksum and compare with the checksum